time to get on to this monthly fourth challenge. And Bill, take it away.
There we go. Better unmuted. Well, great presentations, and I love the interactivity and the ability to interact in questions on the fly and explore. Very, very, very nice, and much more orderly than if we were shouting each other in a room. All right, our challenge today is determining pi by your favorite value. And so I'd like to make a list now of those who wish to participate. So how about either shout out or start to wave? Those who want to participate. Okay, we've got Joel, hold on. I got Joel on the list. Got Brad on the list. We got Dave on the list. We got Strick on the list. Charles Curley, great to see you, Charles. You were at our meeting last night and we didn't chat very much, but glad you're aboard on this. All right, so far I've got Joel, I've got Charles, I've got Brad, I've got Strick, Dave Jaffe, and myself. Anyone else? Okay, outstanding. As you present, remember you can go to share screen. And one thing I've discovered on share screen, as someone is sharing their screen at the top, you'll see a little block about options. And you can pick the zoom level or the expansion level. So if someone's presenting off of an iPad, often the image will be small in the center of the screen. But you can go to that little block up there by the screen share and click on a fill screen. And so no matter what they're presenting on, you'll see a larger view on your screen. Very, very helpful. All right, Joel, let's lead off with you. What was your favorite way to compute pi?
I don't know if my favorite way, I just picked a method and stuck with it. So I'm going to be sharing my screen. Okay, can you see my screen?
Affirmative.
Okay, good. All right, you should see a PowerPoint presentation calculating pi. I'm going to go into that briefly, then show my demo. Maybe I'll switch back and forth. All right, the methods. Well, there are a whole bunch of them. I found Google is your friend. I ended up choosing Nilakantha's method at the following URL. Version of Forth, I used my own Creole Forth for JavaScript. Words can either be defined as JavaScript-based primitives or with the colon compiler. So let me go through the code check. So this is how you do it. You type 100 nilac pi, which I've defined as a word, and then it'll show the pi calculation. Let me go to it. All right. All right, so it's a little bit, might be a little bit small. I get a message box 3.1415924. So I can increase the accuracy by increasing the number. So, whoops, 1,000. I get a better result. A million is about the current limit before it noticeably slows down. So let's try that. As you can see, it's noticeably slower than 100 nilak pi. All right. The numbers 3.14159265358. Well, I won't go beyond there. So I also define another word, CPI, that has no arguments. It simply displays a JavaScript constant math.pi. All right, that's a built-in. Okay, so that should be exactly pi, or as close to exact as you're going to get. All right, here's my methodology. I pre-compute denominator triplets and put them into a JavaScript. This is not a fourth array, a JavaScript one. I calculate individual terms and place into another JavaScript array. Start with the number 3 and then iterate through these terms, alternating addition with subtraction. All right. I'd rather not go into other approaches. I'd rather wait until everybody else is gone first. I did try a couple of other ones. Any questions? Might be a little bit opaque. These are my definitions. Okay, so nilok pi is a high level definition. Some of the predecessor words that it goes through a do loop, and the predecessor words are primitives that are defined in JavaScript. So that's it. Anybody else?
What was the parameter you put in at the beginning? Was that the number of iterations or the number of decimal points?
Okay, let me go to my code and we'll figure that out. It's computed with floating point math. So okay, so what I'm doing is I'm computing nillicanth denominator triplets, and I put it into a global JavaScript array. All right, so that's what this primitive does, do denominator triplet. And then this computes the nth nillicantha term, n starts from 0. And then finally, I do after I've done this step and this step, I add the pre-computed nillicantha terms together. So I accumulate them. So this code does that. And I don't want to, one calculation will interfere with another. So I clear them afterwards. So any more questions? Okay. Might as well take you to the nillicantha method.
Oh, good. Go ahead.
Okay. That might make things a little bit clearer. So you basically have a sliding window of factors. So when I call these triplets. When I compute them, the last term of this one becomes the first term for the next one. So, and I just keep on going. So I can accumulate 1,000, get a certain result. I can accumulate 1,000,000, I get a better result, and it starts to get a little bit slow too. So, any more questions?
I guess that's it. Very good. Thank you.
Okay, I'm going to stop sharing. Um, wait a minute. So actually, how do I do that?
I just did it for you. All righty, we are set. Oh, as a reminder, now we have roughly 1 hour left, so we'd ask the participants to shoot for 10 minutes, and that'll get us on our time budget. So next will be Charles Curley up. Charles, you've got the screen.
Thank you, sir. Let's see if I can get my screen sharing here. Okay. Let's see if I can get rid of that. And I can't see. There it is. Get rid of that. Okay. This is an Atari ST that I used, for developing Forth about 30 years ago. I still have, by the way, Kevin, you'll be happy to know, I still have my original Atari ST. It's 35 years old this year, and it works. So.
Wow.
Yeah, talk about reliable hardware.
I haven't fired up mine in many years. If you, well, welcome. It's so nice to see you. It's been too long.
Yeah. For those who are curious, I'm running Linux and I'm running a Atari, which is a ST emulator, and I have found it very nice, very accurate reproduction of the ST. And so I've got my files-based Forth here. It's called Fast Forth, as you can see on the top line. So CalcPy is a loader that brings it in. This is actually, very little of this is actually my code. Let's see, we've got some loader stuff. That needed is a loader that brings something in if it's not already in the dictionary. Some 16 to 32-bit math functions that simplify things considerably. Leo Brody's random number generator, not real fancy. If you've got a operating system call you can use to generate numbers, it's probably more accurate than this. This is Ting's Newton's method, and my last date on this is 93, so that's probably something Ting did well before 1993. Sometimes it's frightening to see your old code leap back out at you. Sorry about that. But it basically, what it does is it makes a guess and then checks to see if the guess is within the circumference of 1 from the origin. You're basically dropping pixels down on a Cartesian grid, and I'll show you what that looks like as soon as we go through the code here. And little bit of assembler extension to fourth. This is classic fourth. We don't have it. Fine, we'll write the code to do it. The Atari takes certain opcodes on the 68,000 that don't exist and traps them and then executes them as if they were processor opcodes. And that's what this does. So this is direct access to the video level of the operating system. Set up a bunch of variables, initialize them, and then another classic fourth trick, you go ahead and initialize it, and then you forget your initializer to save space in the dictionary. Well, not really necessary. I've got 900 kilobytes of memory available. For those of you who think that 4 megabytes isn't enough memory. Set a pixel. I mean, in addition to doing it in memory and collecting it, we also do the graphics. We get a color at a given pixel and then use that to increment the colors. And so as you go through this, you'll see pixels changing colors multiple times. It's a nice little demonstration of Atari ST graphics as well. Okay, so here, code to draw a line, which we do exactly twice. So we set up a box to display everything in. We can do a pixel, which picks a random number and drops a pixel in there, and I can demonstrate that quickly. So you can see what I'm doing. And now you can see 3 red pixels in there. I hope you can. And picks, checks, n number of pairs, and finally some abbreviations for those. So a real quick run gives you that. So our guess is 3.1. That's cute. Because of the way this code works, you have to divide the second number there, 312, by the number of iterations, or divided by 10 to get your actual pi. I didn't write anything that does that. Take a few more, and it starts getting somewhat better results. And so on. So you can see 2, 3 bright blue pixels in there. Those are ones we hit twice. So you can see how the method works. Is it within the circumference? If not, we ignore it and throw it out. If it is, we use that as a guess and slowly accumulate accuracy. So that's pretty much what I have. I'll be glad to take questions. And where to get this? I don't have the pi calculator itself available, but FastForth is available on GitHub. Just search for my name, Charles Curley. Oh, wait a minute. I think I might have put the pi calculator on there. If it is, you can fire up your Atari and go ahead and use it. So that's all I have. Questions? Answers?
Hey, I'm really impressed with using the Atari ST, but I've got a little question. You're doing a Monte Carlo method, or you're doing a Newton's approximation, or how does it get pi?
It's called Newton's method, and I'm no great expert on the actual method. As I said, I adopted some of Ting's code, so maybe he can
You're
explain
trying
it
to
better
find
than
where
me.
a curve crosses the x-axis?
It's whether a given point is inside a circle.
Is inside the circle. Okay, I understand that method. That's good.
Okay, and you only saw a quarter of the circle. The origin was on the upper left-hand corner.
By symmetry, you only need a quarter, right?
Right.
Okay, thank you.
You're welcome.
I
Any
don't
other
remember
questions?
any of this. Uh,
Very good. And as Strick said, the graphics is very interesting. I mean,
Yes.
I, oh, I struggle learning different versions for graphics, and I'm still trying to plot a straight line. So I don't know. Okay. Next we come to Brad Nelson. So Brad, take it away.
All right, let me go ahead and set my screen. How's that? Can everyone see that?
Perfect.
All right. Oops, click over here. All right, so the method that I used is the Bailey-Borwing Plouffe method. It was discovered in 1995. This is the key formula. The interesting thing about this one is that it was actually discovered by not by a mathematical derivation originally, but by a sort of an exhaustive search through a certain space of summation forms that were sort of known to have the potential to produce interesting constants. And so there's a sort of a fully parameterized version of this that folks dug through and found a number of other sort of fundamental constants, log 2, that kind of thing. And they found this particular one. And there's some others that are sort of more refined than this one, but what's sort of you'll notice the powers of 2 are rather 16 in here. And so what's neat about this one is that it lets you sort of jump ahead and find individual hex digits of pi. And so you can make sort of you can fairly readily jump to an arbitrary position within pi. So you can decompose this if you imagine breaking it out and defining S, which is this, you'll see in the prior thing, each of these others could be defined in terms of this S operation. You can break it into these 4 parts. And then if we sort of drill into S here, if you multiply the S by a 16 to the D, that lets you sort of slide along a hex digit at a time, so that you can sort of fish out certain pieces. And let's go one step further, just sort of breaking it apart now. At the point where you've got the portion that if you multiply by 16 to the D, you'd have some portion that would be in the fractional part and some part that wouldn't be in the non-fractional part. And sort of the way to visualize this is that for each of the pieces that are that you've slid left to higher places, they potentially, because you've got a divide in there, they potentially continue on indefinitely to the right, but nothing to the right sort of influences the things to the left. And so the cool trick here is that if you focus in on the portion that's non-decimal, you can all you really care about if you're trying to fish digits of pi out is to look at them, is to look at the fractional part. So you're sort of multiplying by powers 16 to the D to slide things along, and then all you care about from the part that you shifted past the decimal point is the fractional part. And so you'll notice that this 16 to to the d minus minus k, you can just take the mod of the thing you're dividing by, because you're only concerned about the fractional part. And a power to a number to a power modded is a thing that you can for integer values. There's a very efficient formulation for calculating that. So if you want to calculate, a to the b mod n, you can sort of go one bit at a time through b, and so you basically calculate a to the a squared, and then a to the fourth, and so on. And so you can avoid having to recalculate a bunch of these. And the thing that does is, if you back up here, this lets you do a bunch of these multiplies, and let me state this accurately. For one position that you've shifted over, you could do just integer math, and you can do a divide, and you can sum only the relevant regions of these and fish out a single hex digit of pi. And so what's nice about that is that thinking now in terms of operations you can readily do in Forth, you're doing small operations with only 64 bits of integer precision, but you can slide extremely far down into pi and still get an interesting result. And so, sort of building this up, things that we'll want to be able to print a digit in a particular base. We'll want to be able to do start a multiply and mod, because you'll do that in successive refinement. And then I've got a couple of words here. One thing, when we're all done, if we want to fish things out, we'll want to have a constant for one that we can use for fixed point to sort of pull things out. That'll show up. But anyways, then the next challenge is to exponentiate that a to the b mod n. And I sort of tried two ways to build this up. One is stack based and looks sort of like this. So you're sort of finding the individual a to the 2 to the 2 to the 2 and so on, and then multiplying in at each stage. A different formulation of this can be done using locals, and this whole activity sort of has given me a mild appreciation for locals. I actually, for this particular one, I like the non-locals based one, but as you'll see with the next step up, I found that locals were actually helpful for that. So anyways, you've got the key operation here is this star mod, which is a to the b mod m, and then building on that, the next thing you need to do is calculate those S values. If you'll recall, there's this S summation. And so here the doing it with locals actually ends up fairly nice. You can do you can sort of do each of the two, the left and the right. By right, I mean to the right of the decimal point, to the left of the decimal point. You can do each of those independently. If you do the same, you can do the same thing on the stack, but I found that the gymnastics were kind of rather severe and unpleasant. And so I ended up having to have, because you're juggling essentially 4 things in the stack. So this ended up feeling like a place where locals sort of paid their weight in terms of complexity for what it's worth. And then once you've got that, you just need to, for a particular D value, you can shift over some number of hex digits and then fish out a result. And then that gives you pi, but in hex. And that's sort of only marginally satisfying. You can, for large numbers of digits, you can fish out hex digits. But well, you want to see pi in decimal. So to make it work in decimal, you have one additional challenge. The method doesn't directly generalize to hex digits. What I've ended up doing is taking having a computation that does one cell, so one whole cell's worth of hex digits, and then filling up a region of memory. So I accumulate a bunch of the hex digits, and then I've got a 10th operation that will slide over and multiply by 10, and then I can pick off the decimal portion at the front. So as I'm walking through printing, I can keep multiplying by 10 and fish things out. So the key thing in all of this is that I've avoided any divisions or mods other than single cell size. This one is essentially a multiply by 10 that's multi arbitrary precision, and then that lets me go through it and generate some number of digits into a buffer. I actually just generate them into the unused portion of the dictionary. So here over and then pi fill. So I fill up some number of digits in that space, and then walk over and you basically get about 8 for every cell. You get about 18 decimal digits of accuracy. So I just shift over that many to print it, and then that lets you print arbitrarily large numbers of decimal digits. The divide by 18 is to match the number of digits I had previously. And so here's the whole thing. It's not that much code to do. I am, cheating as it were and using locals and for this, not for the exponentiation, but for the S term. And that's that. And yeah, I mean, it's, so I can do, hex digits, and I can do decimal digits. And I put the dot in there just so I can see it thinking, and then plop. And you can go higher, but and so the method overall is order n log n to go further down the number, because as you have to keep computing everything to the left. Has to propagate over on the left-hand side of that summation, but on the right-hand side, you only have to do the about, I think it's 6 positions or whatever to fill up 64 bits, and you can go quite far in principle. Like this method, you can kind of keep going to some fairly astronomical figures in terms of how deep into pi you go. The way I've structured it here, it's not probably what you would want to do if you actually wanted to leave it grinding on digits of pi, but cool.
That was great, Brad. Bill, did you see Dave Henderson wants to be added to your list of presenters?
Yes, we've added Dave and Joel.
Okay, great.
I want to compliment Brad on his presentations. Clear, and notice almost all definitions are one line. No definitions are more than 2 lines. And that is very Forth-like and very Chuck-like, because I've looked over Chuck's shoulder coding, and almost everything is a one-line definition. So thank you very much, Brad. It's a great lesson in coding. Next up is Strick, and you've got 10 minutes. And as our group is expanding, please stick to 10 minutes, although everybody's done that so far. Thank you.
All right. This should be less than 10 minutes. Share. How's my sharing look?
Perfect.
Okay. This page is wiki.yak.net/1149. I'm also using the Monte Carlo technique for estimating pi. I'll start with a pizza pie, which is round and is the unit circle. It's got radius 1 foot, and it's inscribed in a 2 by 2 foot pizza box. And I'm going to throw darts randomly at the pizza box. And the portion of them that hit the circle, well, the circle has area pi and the box has area 4. So pi over 4 should hit inside the circle. And there's the calculation. So how many darts do you need to estimate pi? Well, the more the better. So my goal is to throw a petadart. If I can do 10 to the 15 darts, let's see how close I get. And in order to be able to do that many, I need to be able to run this in a kind of a massively parallel fashion. So we're going to use MapReduce as our way to do that. I don't know if this is the first MapReduce written in Forth or not. Y'all let me know. And it's actually going to be a special case of MapReduce where the reducer is a combiner. The binary operator plus is all we need, and it's commutative and associative, and so it can be used on each node to combine the results before the final results are done. I'm going to use a fourth in which everything is floating point. I wrote it myself. It's the source is also on this page, and here is the uniprocessor version of map combine. Our mapper takes in a number, and often a MapReduce has some kind of input data. This does not, so it's just the number of the map, 0, 1, 2, 3, up to a quadrillion. And we don't really need that number, so the first thing we do is drop it. Then we spin two random numbers between 0 and 1, square them and add them. And that's basically throwing a dart at the pizza box and finding its distance from the origin. And if that is inside the unit circle, we return true, or 1. And we will do that a quadrillion times. And then we will combine the results of all of those, the true or the false as ones or zeros, with the plus combiner. And that will tell us how many of all those darts hit the pizza box. So map combine looks something like this. If the number of map operations you want to do is your input on the stack, we're also going to put this first 0 onto the bottom of the stack, and that's where we're going to accumulate the combiner results. And then we do the loop as many times as we want, call the mapper, call the combiner. And so finally, to compute pi, if the number of maps is the input on the stack, we pass it to map combine, and the number that comes out, we swap divide by how many maps we did and multiply times 4 and print that. And this is not gonna, if I do a 1 billion, it finishes in about 16 seconds. And so to actually distribute this, I'm going to change this number to just 1 billion and call this entire piece of fourth right here one map operation. And then I will ask my MapReduce, the big MapReduce framework that's distributed, to do it 1 million times, and 1 billion times 1 million is 10 to the 15th. So let's see, I have just talked you through all of this. And after running 1 million of the big maps, in which a big map is running 1 billion of those little maps in that fourth code, this many hit the pizza out of that many darts. And if I divide that and multiply by 4, 3.141592, it should be 65, but we got 71. So our difference is in that digit there. So where did I get my floating point fourth? There's the GitHub for it. There's a compiler, which is a little Python code that generates C++ code. And this C++ class is my runtime. It just contains a stack and a little bit of stuff to do random numbers. And that's my runtime C program that just instantiates the fourth, executes the program on it. And then I had a little different runtime for putting it on the distributed MapReduce framework. So that is pi by throwing a petadart. And I am done. I'm not hearing anybody. People talking?
They're stunned into silence. I sit here smiling with a big grin on my face because the variety of methods we're finding is truly rewarding. Are there any other comments or questions?
So I'm very happy with the size of the fourth program that did it there. And cheating by using a floating point fourth, that's not really cheating all that much.
I'd be
Yeah.
grateful if
I
you'd
don't
send this
consider
link
floating point
to Dave Jaffe for the notes. If you
Okay.
have a link or a PowerPoint or another, please send it on to Dave. If you don't know Dave's email address, send it on to me and I'll forward it. Dave put this in the chat, but I wanted to be sure that everybody heard it because not everybody is reading the chat. So on with the show.
Well, wiki.yak.net/1149, and my GitHub is strictyak if you want to see my little compiler.
Unshare.
Unshare, yes, stop share, thank you.
Okay.
Very good, and thank you. And next up is Dave Jaffe.
Yay.
I'm hoping Dave will send his notes to Dave.
Let's go, baby.
We see your desktop.
Yeah, what? It displayed on the wrong screen.
I hate when that happens.
There we go. Okay, I took a little bit different tactic in this, and I looked at integers and ratios. So, you know, pi is just the ratio of the circumference to diameter. Pi is an irrational number, and we know what the digits look like. And we also can see pi. It was done in skywriting over Stanford in 2012. And that was cool. I was out for a walk when I saw this. That was great. So rather than calculating the number pi, I decided to calculate two integers, n and d, such that n divided by d is the closest approximation to pi. And you can use these numbers in standard force to calculate, you know, the circumference of something using */. And we all know from grade school and high school that pi can be approximated by 22 divided by 7. And 355 divided by 113 is better. But how do you find these numbers, n and d? And so that's what I decided to do. So you can do that by using a language that supports floating point, but I first implemented it on a HP 67 calculator that I had in 1978 that used a little magnetic card, and you can program this device by essentially telling it what numbers to press at, what buttons to press at a certain time. You can record it on the magnetic strip and play that back. So I did it on the HP 67, and it took about 40 minutes to calculate the numbers, which was when the batteries failed. So when I plugged it in the charger and ran it, I was able to finish the calculation. And more recently, I did it in TCL because that was a language I was working with and had floating point. And so here's the pseudocode. You start with the number up on top here, and you define the initial value of n to be just the integer, the 3 part, and the initial d, the denominator, to be the 1 part. And you calculate the error by doing the floating point division, subtracting it from the number, and taking the absolute value. And then you're in a loop where you divide the current n by the current d, and you take a look and see how close it is to the number. If it's more than the number for pi, you add 1 to the denominator to decrease the value. If it isn't large enough, you add 1 to the numerator, and you just continue doing that, calculating the error, and you can do that for as many times as you want, and then just print N and D, and then you're basically done. So it's a very simple algorithm, and here's how it would progress in the first in calculating pi to be 22 divided by 7. You can see how the numerator and denominator increment, and as you do this, you get closer and closer to pi. And this is what the program in TCL that I wrote in 2005 looked like. I tried to run it again this past week and it wouldn't run, so I don't know what I was doing wrong. But in any case, I figured out what the errors were for 22 divided by 7 and 355 divided by 113, which are very good approximations. But to the limit of 16 bits, these are N and D for that, and you get about twice the precision as 355 over 113. But in reality, it doesn't matter, because if you do this in using these values, 355, 113, and this later value, they both come out to the same number. So what that means is that if you're doing, integer math, 355 over 113 is okay. And most of the time you don't need to have this high resolution calculation. So that's my story, and I'm sticking to it.
Any questions for Dave? Come now.
That's the KISS solution.
Yeah.
Yeah. I'm really surprised the TCL program didn't work. They've done such a better job than almost any other language of maintaining compatibility from the early 90s or late 80s.
I used a very old version of TCL that I had. I had to try to run it on an old computer, and it still didn't work for some reason. Don't know.
Oh, Tickle has its niches. I'm using that almost daily.
Oh, wow, cool.
It's like when it has to be scripted, Tickle, you need a GUI, TK, gets complicated, excellent, object orientation, add an I in front of each and you're good. Need to drive something command line style, expect. Need something done fast. C plugins into Tickle or C++ or the other way around, embed an interpreter into a C++ environment, and if you feel like it, you extend that again. And then on top of everything else, you can still, with that setup, you can still drive a single board computer running forth in case you don't feel like feeding anything complicated from the outside. They have their use cases. But they're, and they are definitely not dead.
Right. So I was using TCL because that was the language that programmed the driving simulator that I was using, and it's a very powerful language, and one that worked well for this simulation application.
Well, great. Thank you very much. I reminisce and say you're using TCL because you use what you have and you use what you work. And anyway.
You use what's easy, what does the job. The tool has to fit the job.
And thank you. Okay, next up, Dave Henderson, your turn.
Can you hear me?
Works fine.
Okay, great. Okay, I'll show right here. Share my screen. Okay, can you see? See my screen?
Yeah.
Wait.
All right.
Yeah,
Okay.
Yeah, you're good.
Okay. First off, I was going to show I think several folks have done the Monte Carlo method, and so I very quickly put together to calculate pi, does a million iterations in forth, and I end up getting I use VFX forth, and I ended up getting, I don't know if you can see this, but 3.1415927. It takes a billion iterations, takes a few minutes to do on my PC here. And that was interesting. Learn a little bit more about how the floating point works in forth. I haven't used it too much. I've been able to use mostly integers in all the work I've done on forth. So the next thing is I found a nice video on YouTube about using the Mandelbrot set to compute pi. Mandelbrot's set is normally used to create pretty pictures that used to be on posters in college, and a very simple formula here that you iterate through, and but you can also use it to generate digits of pi. You use values past the cusp, which is c greater than 1/4, and these values will diverge, but we can use it. You don't get any pictures out of it because of that, but we can use it to generate digits of pi in a pretty slow way. So the algorithm we use is to pick a really tiny value of a small epsilon to add to that value, to add to 0.25, and then we iterate through it, and we stop when the result reaches 2. And the interesting part is the number of iterations you end up with will contain one or more digits from pi. And so pictorially, here's where here's where you're getting the here's where you start, and you just move a little bit to the up on the x-axis, calculate a constant c, and use that. And here's what I got when I ran the program. And if you use smaller and smaller epsilons, you end up getting a pretty good number here. But it takes, like I said, it took several hundred million iterations to get to a decent value of pi. So the caveat on this is the reason it was difficult for me to implement is it about 30 digits of precision for the math operations. And that's beyond the range of most of the floating point representations. So I wrote it in forth, I wrote it in Python naively using the floating point sizes that I had there, and didn't converge on a value of pi. I ended up using mpmath.org to have it for a variable arbitrary position for floating point arithmetic. Here's a listing for it written in Python, and I import the mpmath and use its operations to add the epsilon, and I tried it for different epsilons, and do a multiplication here, a square, which is multiplying by itself and adding the value, and converging, stopping when it's reached 2. And there's a great number file video that describes this. The person's a lot better looking than I am. And the math.org, the mpmath library is available here, and info on the Mandelbrot set is, of course, on Wikipedia. And that's all I have. Thank you very much for letting me present.
Any questions?
Yeah, it's coming up with approximation to pi in decimal because your epsilon is in powers of 10.
Yeah, you're absolutely right. You're correct. I think there's a binary one where you start out with powers of 2, and you can do it that way too.
Uh-huh. All right, that's very cool. I never heard of that. I'll have to look for the number file.
Cool.
I liked your initial statement. The usual use of the Mandelbrot set is to.
Yeah, there's a lot more to it, and that's like the trivial use of it. But I had no idea you could use it to compute pi. That was very interesting to me.
Again, we are having a far-ranging exploration in mathematics. I, 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 I'm laughing. I would have never thought of finding this many approaches. What's next up is Joel Sprentz. Please come now.
Okay, let me share my screen. Oops. And so my strategy began with looking around like everybody else did. Because I started with fourth on machines with 4K of memory, I was thinking I should avoid floating point and long integers and trigonometry and the stochastic methods I was aware of, but I thought they would take too long, although several people have proven that they're just fine. And I was looking for something that I could understand with my engineering education. Wasn't a math major. Sample code is always a plus, and clear explanations. So I found this paper which describes how to generate the digits of pi one at a time. The paper is the first reference here, and there were several others sources that led me back to the paper. I guess the insight from the authors was that if pi is this infinitely long number, we can represent it as the second formula that we see here, essentially a number in base 1/10 here. And they found a convenient series for pi that translates to a very similar looking formula where all of the constants are 2 as compared with the previous one where we had 3, 1, 4, 1, 5, 9, and the base was constant. In their approach, the value is 2, 2, 2, 2, 2, but the base is a third, 2/5, and so on. So all we have to do really is convert from this 2, 2, 2, 2 in that kind of odd combination of bases back to the 3, 1, 4, 1, 5, 9 in base 1/10. And it's very easy. You know, we don't know what the next number is in this pi series, but we do know the next number is going to be a 2 and then another 2 and so on. And this is 1, 2, 3, 4, 5, 6 up on top, and then 3, 5, 7, 9. There's a pattern here which is pretty easy to work with in fourth. How many terms do I need? In this case, I've got 6 digits showing, so they say I would need 10 times that. 60 divided by 3 is 20, and 1 for good measure. That's not how they derived it, but that's what I'll say. Sample run for 1,000 digits looks good. I compared it with a source on the internet, and I formatted my output to match their output so that I could come down and look at, say, oops, the bottom row. See if I can get back to that. I learned not to click on that. Okay. So I could look at the bottom row, 888 or 88, 23, 53, 78, 75, and then go back down here in the check values, 88, 23, 53, 78, 75. I've run this through diff on Linux, and my answer is good. So then, because I was inspired by Bill last month, I ran it for various numbers of digits to see how long it took. And not surprisingly, it squares with the time squares, scales with the square of the number of digits, because that earlier formula for how many terms in the formula I needed was linear with the number of digits, and the number of iterations is also linear, and so we have nested loops, and that gets us there. I'm running on a G4 version of 4th on a Raspberry Pi 4, so faster computer would get a better result, I guess. Let's run it. 1000, oops, G4 pi.fs 1000, and so it comes up pretty quickly. And the code will be distributed later. Nothing remarkable in the code, I guess, but I'll answer questions.
I really
Hearing
like
none.
the idea of thinking about it in weird bases. That's cool.
So my great relief is no one else chose this method. So back to you, Bill. Let's see if I can turn it back.
Thank you, Joe. Any other questions? Come now. Of the bunch, it looks like that one's the most fourth-like. I loved getting a lot of output for a minimal input. All right, do we have any other presenters before I wrap up? I've got one to come next. All right, 3 pieces of pie, 3 different approaches. The 3 approaches. First, I'm going to use integer math, computing pi to 5 decimal places, floating point to do it to 14 decimal places, and then a trig expansion to 16 decimal places. This are grossly inferior methods because they're limited strictly by the stack width of the computer. So I found this identity. The 4 times the arctangent of 1 is equal to pi, and finding a proper expansion for arctan expands down what you see below. Pi is 2 times the following expansion. So you look at the terms, because that's where the computation is done. The inner term is the current loop index. Let's look at the outer, that's right, okay. So that inner term is the loop index divided by 2 times the index plus 1. So for an index of 3, the denominator is 7, and that's computed simply by the dupe 2 times 1 plus star slash. Each expansion then takes the previous factor and then does a dupe root plus swap, and that expands you by 1, and you just repeat. So here's a pseudocode. We start with a summation of 1 and a product of 1, and then we do the loops where we do that inner factor and then outer factor. And then the summation is repeated, replaced by the new summation, and the current product is replaced by the new product. This is all done on the stack. Repeat that a number of times. We drop the product, and the final value is multiplied by 2. So here is the method. We've done it on integer fourth, so therefore the normalization factor is 100 million. That is, the number 1 is represented by 100 million. And you see it's very simply the run integer, run I, is starting with the initial factor. You run through the loop expansion, in this case 25 times. The loop expansion is shown down below. 25 times later, you get an answer. You then multiply by 2. And here are the iterations. So the initial n we just guess at 1, and the error factor is 0.333. We add that to get 1.333, and then repeat, and the error factor is 1.333, and then adding error, add error, add error. Of course, the error gets smaller and smaller, and when the error approaches 0, down in the bottom right corner, we see that our integer calculation got pi correct to 1, 2, 3, 4, 5, 6 decimal places. Right, 6 decimal places. And then the CPU value is by the floating point chip on the computer. All right, here is the, there we go. Now, instead, in this case, we're using the same algorithm, but we're doing it by a floating point, which adds resolution. In this case, we start out with a floating point integer 1. We do 50 iterations. Do the same expansion, except translated into floating point. And since there's 50 iterations, I've omitted the central portion. Again, the first n0 is 1. The error factor is 0.333. Add them together to 1.3. You see the second error factor on the second line on the right is 1.333, and repeat, bang, bang, down, all the way down. 50 iterations later, our error factor is now down into 1.8 times 10 to the minus 15. And in this case, we get pi to, I believe, 16 decimal places, which is the limit of the resolution of the floating point that's used. The last method I stumbled onto some time ago, and I don't know the reference on it, where it came from, but it was it was pointed out as being clever, and it certainly is. So the previous method that we used was this expansion using arctangent, and I looked at that and I said, that's a lot of work. So I want something with a very simple expression. So I want an expression that is pi equals to some number plus some error factor. So the function of n is the error factor. And by rearranging, we see that if we take pi and subtract our current value, the error is the function of n. So as the function of n goes to 0, the n0 value will approach pi. So how do we make the function of the current factor 0? First, we don't know the initial value for n, so we will just guess and do repetitively. And then that just leaves, how do we determine that error factor, the function of n, or the function, and to make that function of n equals 0. So when n0 is pi, the function of n0 has to be 0. So here's our challenge. Mentally, before I go to the next 2 slides, what function of pi is 0? Think about it. Well, if you look at pi squared, no, that's not 0. If you look at the log of pi, that's not 0. If you look at e to the pi, that's not 0. Besides, we need a cyclic function because we're going to do this iteratively and we want it to approach pi. So how about for a cyclic function of pi, how about tangent? Well, we see that at 0, where the green arrow points. At 0 pi, the tangent of pi is 0, but the functions are not continuous and would be, essentially impossible to compute with. Aha, the sine. How about the sine? The sine of pi is 0, and the function is continuous. So here's a geometric solution. If we guess at an n0, the green arrow, calculate the corresponding sine of n0, the red arrow, And then that's our error function. We just add the two together. Now we have N1. From N1, we calculate the sine of N1. We get a new error term. Add that to N form N2. We're getting close. Now we compute the sine of N2 and we add it to N2. And after enough iterations, we reach pi. So the mathematics on this is trivially simple. In the place of N0, sine N0, all we have is dupe, sine, and add. F duplicate, F sine function, F add. That's all there is. We put that in a wrapper where we will do it 6 times. We'll start with a number of 1, 1E0 is 1. We'll repeat that expansion 6 times. Here's what it looks like on a D chart that I introduced last time, which we all know and love. The wrapper at the top, run pi, the expansion, the do loop. And here are our terms. I've placed that sine function above so you see geometrically roughly what we're about. The first N0 is 1. The sine of 1 is 0.84. We add that to get the N2, which is 1.84. The error term there is 0.96. And notice the error terms now are converging. We're on the downhill slope approaching pi. After 5 iterations, the error factor is 0.00000001419. And we reach our final N value at the bottom left. And the next error factor, if we used it, which we don't, is 1 times 10 to the minus 16, truly a small number. So by this expansion, we've gotten pi to 16 decimal places. Now, I realize that any calculator that can program, that if you can do sine, it can also calculate pi. So we're really doing a lot of cheating here in that the same approaches that we're using to calculate sine can be used to approach pi. So the justification for this is that I'm interested in finding shortcuts or clever techniques. And this one was finding a method for pi that involves 3 calculations and definitely done in 2 lines of code. So this method also gives more clarity and it lets us get an insight to the transcendental functions. And it's, I think, much more intuitive than you see with a number series. So do we have any questions or comments? I see we're all sitting here in stunned silence. That's very, very good. Thank you for the thumbs up.
Yeah, that's a big wow for everybody.
Great meeting today. Also, I'll turn back to Kevin now. But and of course, next month is 4th day, and we expect to have a rousing turnout. And we'll see. We may or may not have a challenge next month. It depends on the time factor. So back to Kevin. Thank you very much.
Well, Bill, this was an excellent challenge and a lot of fun and a lot of creativity. So thank you.
Yes, it was great. I just wanted to mention there was some comment about if you want it faster, use a faster computer than the Raspberry Pi. The number I could find quickly for the Raspberry Pi 4B is 13.5 gigaflops. For scale, the Cray 1, I believe, is 160 megaflops. So it's all relative. Dr. Ting, are you there?